In this module, we're going to talk about the Born-Haber cycle. So this is in comparison to what we just talked about with the Born-Londe equation, which was an equation built upon having ionic having ions and calculating the lattice energy. So this is going to be a way to calculate lattice energy that does not depend on having an ionic material and using those same equations. So let's take a look at the Born-Haber cycle. So we use this Born-Haber cycle to calculate lattice energy, and instead of doing it by having ionic assumptions, we're going to do it by looking at the enthalpy of the reaction to form this material. And so this is why it's kind of called a cycle, is because we're looking at the cycle of creating this material. So this is what a very general Born-Haber cycle would look like if we're creating a MX compound, where M is the metal, X is the nonmetal, and we're looking at the solid. So what we want to try to get is this lattice energy, and that is basically defined as taking the metal ion and the nonmetal ion, so the cation and anion, and forming, so those two ions, and forming the solid, right? If I take those together and form a solid, that's the lattice energy. So we can calculate this by looking at a lot of other steps that have to go into this reaction. And so we can look at, so we start with the metal, which is typically a solid, the nonmetal, which is typically a diatomic gas in this case, and we can look at the various steps of taking those elements in their pure states and getting to this reaction. So going from this to the solid is the formation, the enthalpy of formation. So we have that here. To go from the metal solid to a metal gas involves vaporization. To go from the diatomic gas to a monoatomic gas, we have to dissociate, and then we ionize both of them. And so all of those factors go into basically an enthalpy of this reaction. So we can write it as the enthalpy of formation, which is going to be exothermic, is equal to the sum of all of these other energies. So the lattice energy, which is exothermic, the ionization energy, so this is again metal to metal ion, the electron affinity, which can be either endothermic or exothermic. This is taking the nonmetal element and making it an anion. So that's electron affinity, so adding an electron, and that can be either, again, endothermic or exothermic, so positive or negative. We also have the dissociation of that diatomic atom, or molecule, sorry, and then the vaporization from the solid to the gas. So we can basically rearrange this and solve for the lattice energy, which is what our goal is. So this is the generic reaction, but you can very easily do the same type of schematic or Born-Haber cycle for any other type of material like sodium chloride or any other material that we want to examine for this process. So let's kind of take it step by step and look at the sodium chloride as an example. So sodium chloride, the nonmetal is chlorine, and its natural state is Cl2, so diatomic. So if we want to get that into Cl, then Cl gas, then we have to dissociate this molecule, and so that is going to be the dissociation energy in this equation. For sodium, sodium's natural state, standard state, is solid, and to get that to a gas, we have to have the heat of vaporization, which is readily available. The ionization energy, so this is to find the energy to remove that electron from, if we go back, we're ionization energy, we're looking at removing an electron from the metal to create the cation. And so we can get values. This is actually a table from our book. So we can get the first or second ionization if we're trying to remove multiple electrons. And then the electron affinity, this is adding an electron to the atom. And so this table also from our book can do that. So in this case, we would be looking at chlorine, which shows you that going from Cl to Cl minus, so adding one electron, is exothermic, and it's exothermic by this amount. All right, so all of those things together, we can also calculate the lattice energy. So what I want you to do is same thing. See if you can draw up the Born-Haber cycle for this material, and more importantly, calculate the lattice energy, which is similar to the last exercise we did, but using the Born-Haber cycle that you've created, see if you can calculate that lattice energy using this approach. All right, so now that you've had a chance to approach this problem, let's kind of go through this step by step. So I was asking for the lattice energy, but I'm going to start with actually drawing the Born-Haber cycle for sodium chloride. And if you need a sort of starting point for this, feel free to use the generic one in our textbook as a sort of guide, right? The MX goes that reaction, and see if you can kind of substitute in what we have here for sodium chloride. So that's what I'm going to do. So our end goal at the end of the cycle is going to be an NaCl solid, right? So to form that, which is going to be the enthalpy of formation, we have to go from our standard state for each of those elements, right? For sodium, that is also solids, a metal, plus the standard state for chlorine is going to be that diatomic gas, right? So this, right? So that's our kind of standard state. So it looks pretty similar, only instead of MX, we've got Na and Cl. All right, so let's kind of write out the steps then. So for the sodium, we see that it's solid. This has to go to gas because we're going to talk about ionization, and that's gas to an ion. And so this is E vape. So just a quick note here, if you were doing this for another material, look at the standard state. If the standard state is liquid, then you're going from liquid to gas, and so that's going to change what this is. It's going to be basically that liquid to gas instead of solid to gas. So you're going to be talking about vaporization in that way and not from solid. So that's important. And then we need to break the diatomic molecule up, and so this would make Cl gas. So this is going to be the dissociation, or E-dis. And so to get this into an ion, we're making, this is going to be our cation. So that means that we're stripping an electron to create this positive, and instead of M, sorry for that, it's going to be Na plus, right? And this is going to be a gas. So this is the ionization, so E ion. Here, we're going to create a cation because it's the nonmetal, and so we're going to take that electron from here, right? That electron is going to be transferred here, and we're going to get to, sorry, did it again, Cl, not X. So it's going to be Cl minus 1. So this is another area where, in this case, these are unit charges, right? We're only dealing with the transfer of one electron because that completes the shells on both Na and Cl. In another compound, it might be, minus 2, plus 3, it can be any charge. So you do have to look at the configuration and what creates a stable compound in those regards. And so then our lattice energy is going to be the addition of this ion plus this ion to create NaCl. So this is our E lat. Right? So, you don't have to draw this for every single problem you do this way, but this is just a good way to sort of visualize the kind of equation of the formation enthalpy, which can be which is exothermic, is going to be equal to the lattice energy, which is also exo, plus the ionization, which is endothermic, plus the electron affinity, which can be either, plus the dissociation energy, which is endothermic, plus the vaporization. So it's just a visualization of this equation. So you don't have to do it every time, but I thought I would show you this specifically for sodium chloride. Okay, so if we're after the lattice energy, then all we need to do is rearrange this very simple equation. And so solving for the lattice energy means that we take the enthalpy of formation and then subtract all of these other terms off of it. So the E ion minus EA minus E dis and minus E vaporization. And we do need to keep track of the units here. So exo and endo and all of these, we need to make sure that we keep track of those. So this equation now, if I just get rid of this one here, the Born-Haber page, and we just look at this, now we need to basically go through and find these values. So most of these you don't have to do any sort of calculation, but you are going to have to find the values. So if we look at our textbook, I'll go to the first one. So this is in our chapter 2 of the textbook. You'll see that the enthalpy of formation for rock salt at standard state, which is 298 K, is actually just given to us, right? If it's not in our book, then you might have to find it in a table or online or so forth, but here it's just given to us. So that's going to be, this value is minus 411 kilojoules per mole. So we got to keep track of the units as well. All right, so the next thing, let's look, kind of do it in the order of the book for us as well. So again, if we go to the next section here for dissociation energy, so E dis, we see that, again, this is looking at our specific example. For this, it's giving us this value as endothermic, so that's going to be plus, and it's going to be 121 kilojoules. So let's go ahead and write that one in. So this is plus 121 kilojoules per mole. Oh, sorry, that's the wrong one. So this is dissociation energy. Gotta make sure, I gotta make sure I keep track of them. All right. So still going in the kind of same order as the book here, is if we look up the heat of vaporization, it's got that for us, latent heat of vaporization, and it's listing it for us as 107.3, and this is again endothermic, so it's a plus. So keeping track, vaporization, so we've got plus 107.3 kilojoules per mole. If we go to the next one, ionization energy, down here, so I'm just going in the order of the book, this is going to be, if we're talking about ionization, we're talking about completely remove an electron, so that's going to be the cation. And so this one is back here. It listed it for us as well, but I just wanted to show you where it got the ionization energies. So this is table 2.2 on page 21 of your textbook. And so if you kind of go through, and we're looking at removal, and so that's going to be sodium, because we're going to have sodium plus, And so if we go and look for sodium, where is our sodium here? Here it is, at 11. So it gives us the first ionization energy of 5.139, and this is again the removal of that one electron, but this is also in electron volts. So let me go ahead and write that down for us. 5.139 eV, and we'll look at converting that in a second. But let's get the last term we need here, the electron affinity. So if we go back to after ionization energy, we're over here at electron affinity. It actually gives us the table right near this. And so in this case, we're done with sodium. So we're looking at chlorine and we're forming Cl minus. We're adding an electron. And so that value is going to be 348.7. It says it's exothermic, so it's negative. So let me go ahead and write this value for us. 348.7. This was in kilojoules per mole. And this was exothermic, so I'm going to put a negative there. Maybe circle these so I don't get them mixed up. All right. So I've got all my values, and really all I need to do now is convert and then add it all up to get the lattice energy. All right, so if we take electron volts here that we have for the ionization energy, our conversion, if we want to convert that to kilojoules per mole, is going to be 1 electron volt equals 96.487 kilojoules per mole. So that's our conversion. So if we run that quick number, we get 5.139 times 96.487, and we get 495.85 for our value for the ionization energy. And I just want to check that real quick against what we have in the textbook, since they gave us that value. And so if we look in that section here, even though the table was in electron volts, they gave it to us in the text as that same value of 495.8 kilojoules per mole. So just to check on a conversion to make sure that that worked. All right, so now that we've got all of these values converted and looked up from the text and tables, let's go ahead and plug these all in. So we've got minus 411 kilojoules per mole for the enthalpy of formation. We've got minus the ionization energy, which we just calculated down here. So that value is positive 495.85 kilojoules per mole. We've got subtraction of the electron affinity, which is also negative, so that's going to be plus, so 348.7 kilojoules per mole. So all the units are the same at this point. And then minus the dissociation energy, which is 121 kilojoules per mole. And then minus the vaporization, which is 107.3. So if we do all that, really simple arithmetic, we get a value of negative 786.45 kilojoules per mole. So using the Born-Haber cycle, we get a value of negative 786.45 or 0.5 kilojoules per mole. Okay, So now that we've calculated the lattice energy in two ways, from the Born-Haber cycle, which we have here, and so this makes no assumption based on whether a compound's ionic or so forth. In the equations, you see that we're assuming it's an ion, but it actually doesn't make that big of a difference. And then we had the previous calculation from the Born-Lande equation, and we got this number of minus 750 approximately. So we see that the two numbers are pretty close, right? Like I mentioned before. But there is a discrepancy of about 35 or so in this value. And so in this Born-Lande that we did here, we saw that we did assume ionic bonding Coulombic interactions in that way. And so differences between these two can kind of be accounted for in the assumptions that we make for the Born-Lande equation as opposed to this, which is all empirical. So all of these values that we calculated for the Born-Haber cycle are empirical expressions of all of these values. So we're not kind of assuming and using a model for it. And so there's a discrepancy of about 35, and that can be due to that. And so if Born-Lande assumes that it's ionic, and this does not, the discrepancy in a lot of cases can be an expression of some of the other forces that we're not accounting for, like covalency or potentially secondary bonding and other things that are outside of the ionic calculation. So that's just something to keep in mind when we're doing these calculations. When we do the Born-Lande equation for very covalent materials, we see that the answer is much different than what we have for the Born-Haber cycle.